as we have seen earlier, in parallel to image and video deepfakes, audio deepfakes have also fast development in recent years, with many commercial services emerging. Here is an example of a synthetic audio of the famous podcast host Joe Rogan, generated by a Canadian company known as DISA. It shows the state of art of the audio synthesis quality.
Healthy local ingredients, farm fresh ingredients. Some of you just need to improve the quality of your existence on Earth. You got to do the right things.
Now, as human ears cannot tell the difference from the real and the deepfake voices, we need to develop detection algorithms also for audio deepfakes. So for this purpose, we need to look into the fundamental differences between human voice generation and the algorithms that are synthesizing deepfake audios. So suppose we have an audio signal like this. The question is this come from a human voice recorded on a certain device, or it was generated by deep neural network synthesis algorithms like Google weaponized? Okay. So for this purpose, I think we take the audio signal, and it is important to actually transform it into the frequency domain using the Fourier transform. So as you may have known, Fourier transform is taking the same audio signal, but just decompose it as a linear combination of different harmonic components, represented as a complex exponential function in both in both time and frequency. Okay, so a very popular and useful representation of audio signals in the frequency domain is known as the spectrogram, which is a short-time Fourier transform of the audio signal. So on a spectrogram, what we'll see are time dimension and frequency dimension. Different audio signals will just be decomposed as time-varying harmonic components on the spectrogram. Okay. Now, for a particular audio signal, usually we look at their second-order correlations in the spectrogram or the local energy levels of spectrogram. This is because human ears are particularly tuned to the power spectrum, the second-order statistics of audio signals. And we heard those words based on the local energy level of the audio signal that is reaching our ears. But this is also the problem that we can make it difficult to tell the difference between the actual human voice from those synthetic ones, because those generated audio deepfakes have exactly the same second-order statistics as human voices. So if we just look at the local power spectrum, we're not going to be able to differentiate these two types of audio signals. So we need to look into something of a higher order of the signal correlations. And in particular, in our work, we have observed that the human voices, the actual human voices, and the synthetic voices can be differentiated using their differences in the local phases, which cannot be captured by power spectrum. And we need to go beyond second order signal statistics and go to something with higher order. So before I jump into the mathematical details of this kind of higher order signal statistics analysis, let me give you some intuition why this happened. Now just consider the actual voice or real human voice, how we get that signal, right? Suppose we have one person, two people in the room, one speaker, one listener. Of course, we can replace the listener with a microphone. Now, to actually record a sound or hear a sound, what happened is sound transmit as a wave in the space, and it originates from the speaker's mouth and transmitted in space, reach the ear of the listener or the microphone. But one critical effect here is the fact that sound doesn't transmit from the source to the target with one single trajectory. As we can understand, the two speakers, the speaker and the listener in the same room, so the sound wave actually starting from the mouth of the speaker reach to the listener's ears goes through by different paths. Some of these are direct paths, some other are just, first the sound wave go to the ceiling, the walls, and then bounce back into the listener's ears. So this means that from the listener's ears or the microphone, the receiving device, it gets sound waves reaching it from different trajectories with different lengths. This different lengths correspond to different arrival time of those different copies of sound waves reaching the target, reaching the destination, okay? And different arrival time represented in their signal forms corresponding to a slight difference of local phases, all right? So human auditory system have developed in a way to ignore the slight differences of local phases. So essentially, we cannot hear it. As humans, we cannot hear the differences in local phases, right? In comparison with other animals like the bats. The reason is that we make sounds mostly for having a conversation to convey certain message and the information to the destination, to the listener. So if the listener's ears is sensitive to the local phases, we're not going to hear a single voice. We're actually hearing a mixture of the same signal, slightly changed with slightly different local phases. And the end result is we cannot, our auditory system will have a lot of difficulty of extracting out the effective message in the audio. So our ears just developed an insensitivity to this kind of local phases. So this is exactly being utilized in generating those synthetic audios, because the synthetic audios just need to match up the local energy level or second order statistics to make it indistinguishable for our ears. On the other hand, if we have a way to extract local phases from the audio signals, then we can make use of that and use it as an apparatus or device to look into the differences between the actual human voices and the synthetic ones. So to be able to do that, we need to go, as I mentioned earlier on, we need to go beyond second order statistics, and we need to look for something with higher order statistics. And we found a tool that is have been developed in signal processing for the past 4 decades, which is known as bispectral analysis. So put very simply, the bispectral analysis look for third order correlations between the harmonic components in an audio signal. So instead of looking a pair, we're actually looking correlations between 3 different frequency components. The actual mathematical definition of the bispectrum is given like this. So you notice that instead of multiplying a pair of signal with different frequency components, we're actually in a triple of them. Okay, and we can normalize the bispectrum into what we call bicoherence, so that the number will be between 0 and 1. So the bispectrum, because it's this higher order nature, it becomes very sensitive to local phases, and that is the reason we use it for to build features to differentiate between real audio, real human voice from synthetic voices. Okay, so this is what I'm showing you here are some of the bicoherence, visualization of bicoherence from different types of audio signals, okay, including human voices and other types of audio voices created using different models. Because the bicoherence itself is a complex value. So we look at both the magnitudes and the phases. No, this is not local phases of the audio signal, but actually the phases of the bicoherence function itself. Now, this visualization shows a strong contrast between those audio signals coming from real human voices and all the other audio voices or signals coming from the generation models. Okay. Now we contribute all these differences to the local phases, in the differences of local phases in those images, sorry, in those audio signals. As we know that human voices is captured using microphone in a real environment, there will be somehow more random local phase correlations. On the other hand, as we know so far, most of the generation algorithms are based on a neural network model with a fixed architecture. So there is a stronger correlation in those models that we can actually exhibit, expose, use the bicoherence as a tool. Now, based on this magnitudes and the phases of bicoherence, we just built a set of very simple features based on the top 4 higher order cumulants from the bicoherence magnitudes and phase themselves. And this leads to an 8-dimensional feature vector. Okay. When we actually build a classifier on top of that 8-dimensional feature vector, it turns out that even with this very simple model, we can achieve some good classification performance. What I've shown here is a 2D visualization of those 8-dimensional features using a t-SNE, a nonlinear visualization algorithm. And notice that samples from human voices tend to cluster in the center that is covered by this oval. And different type of generation algorithm tend also to cluster together in this space. And more importantly, they can be very well separated from those samples coming out of real human voices. So we just build a very we can build a very straightforward classifier, SVM based classifier, and we can achieve a classification performance of around 90% of the time. Okay. Now, even though these simple methods seem to work well on this data set we have, its overall general performance is still need to be tested on a larger data set with more types of audio generation models. And also, it is, as any detection algorithm we have talked about, it is possible to actually circumvent this detection. For instance, if the generation model people making generation models understand the fact that this is based on our method works by looking at local phases, the specific relation of local phases in those generation models. One idea is to just randomize the local phases in those synthetic samples, and that could potentially circumvent the detection, this simple detection method. So I think this is the same kind of situation for all the detection methods we have talked about so far. There is always a dynamic competition between the generation and detection. Right. Now, we have been talking about a lot of development in the counter technologies, especially detection algorithm for deepfakes. So one thing we would like to make happen is to, provide all this detection algorithm, make them accessible to the end users, right? So actually, the fast development of deepfake detection methods can be seen from the number of research papers on this topic, which roughly doubles every year. as some surveys show, right? And this means we have many effective detection methods, and they even have readily implemented code on open code sharing platforms like GitHub. Now, for a user who just wish to analyze one single image or audio or video, she has to find the code on GitHub, download it to her computer, and then set up the environment, and then compile it before she can actually use the code for the actual analysis. So the whole process is still quite cumbersome and inefficient. The alternatives are a few services that provide analysis of authenticities of digital media, specifically targeting deepfakes, such as the Reality Defender from Microsoft, and some services provided by a few startup companies. But these platforms usually use proprietary detection algorithms, and so which may not be able to keep up with the pace, with the fast development of deepfake synthesis algorithms. So it is for this reason that we developed the DeepFake-O-Meter platform, which is an open platform to bridge the gap between the state-of-the-art deepfake detection methods and the user. Our design philosophy is to have an open source, online, and user-friendly interface to various deepfake detection algorithms as a portal. Okay, these algorithms are incorporated into the platform using a set of lightweight API wrappers. So the purpose here is, for developers of deepfake detection algorithms, this platform provides an API architecture to wrap individual algorithms and provide the possibility of run this as a service on a remote server. For researchers of digital media forensics, this is an evaluation benchmark platform, and it can be used to compare performance of different algorithms, detection algorithms on the same input. For the end users, as I mentioned, this provides a convenient service to analyze deepfake media with multiple state-of-the-art detection algorithms. And the platform also guarantees secure and private delivery of the analysis results. So I'll talk a little bit of the details of the use of this platform subsequently. So the DeepFake-O-Meter platform is consisted of a front end, which provide a web-based user interface and the temporary storage space for the user to upload files and download analysis results. The backend of the DeepFake-O-Meter is a computing server equipped with multiple GPUs to perform the actual analysis using individual detection algorithms, which are wrapped around as containerized as Docker images. Now, these Docker images are created by wrapping these Docker containers are created by wrapping individual algorithms using a simple set of Python-based classes and APIs. In between the front end and the back end, there is a task scheduler, which continuously check the task queue and move tasks to the back end for running based on priority. And also, whenever the analysis results are ready, the task scheduler will also move it back to the front end. So the front end and back end share the same storage space through an NFS file system. Okay. Now we choose this model to accommodate the asynchronous communication between the user and the system. Some of these detection algorithms actually take longer time to finish. Third-party detection algorithms will take some time to finish. So we don't want to hang the user on the front end so that we bring this asynchronous mechanism to make the computation run in background while the user users are free to do other things in the same time. Okay. All right. So to access DeepFake-O-Meter, you can go to the following website hosted by the Multimedia Forensics Lab at UBuffalo, my group. So we keep the user interface very simple. The first part is to upload an image or video or audio file to be analyzed. So the user can choose either type in the link to the image or video files on YouTube, other online video hosting websites, or they can upload the file directly from a local computer. After that, the user can select detection methods to be run on the We currently support 11 different state-of-the-art deepfake detection methods. These are for face swapping videos, GAN images, as well as synthetic audio files. For instance, we have included the 2 top performing algorithms from the Facebook, Microsoft deepfake video detection global challenge hosted on Kaggle last year. And the user can basically choose any subset or all of the algorithms to run on the input. Now, these are the details of the 11 different detection methods that have been incorporated into the DeepFake-O-Meter platform. We plan to add more methods in the future so that this platform will be kept up to date for the current deepfake generation algorithms. And we'll also augment the types of deepfake media that can be analyzed by this platform. All right. So after detection methods are selected, the user is required to provide an email address as well as a PIN code. The reason for this is to create a unique name for the analysis results. So the same user can potentially upload several different analysis tasks for the system to persist. And the PIN code just makes sure that every task will be different from each other. Okay. After the confirmation, the user will be led to a confirmation page on the website and will get an email at the address provided early on. Okay. And when the analysis is ready, the user will get another email at the address provided provided earlier on, and the analysis corresponds to a zip file with detection results. Okay. The analysis results contain what we call frame for videos contain frame level detection, frame level integrity scores. These scores corresponding to the confidence of the detection algorithm. The higher the score is, the more likely the frame come from a real video. On the other hand, if this number is lower, then this video is likely to come from a synthetic algorithm determined by the detector. So we also report an aggregate score for videos and audios, and for images, you will get a single integrity score. Now, this interface currently is still very crude, as you've seen. So this is an input, this is a real video, this is the corresponding fake video, and this is analysis of that fake video based on 4 different methods that have been incorporated into the DeepFake-O-Meter platform. And you can, once you have this analysis, it is very easy to see how well each of these algorithms performs and compare with the other algorithms. Like in this particular case, the method WM by the way, it is the second best run of the second place in the deepfake detection challenge. Works pretty well. Well, the fake video is not picked up by the other three alternative detection algorithms. Right? So we are trying to subsequently augment this the return analysis result to make it more useful and informative for the users. So far, we have covered several different type of deepfake detection algorithms for different media types. Now, even though we have state-of-art deepfake detection algorithms that seem to work really well on benchmark data sets, there are still a lot of room for improvement. In particular, there are challenges to all the deepfake detection algorithms. The first one is the lack of explainability or interpretability. Usually, the most effective deepfake detection algorithms are based on some black box type of deep neural networks. Given an input image, audio, or video, this black box deep neural network model will output a predicted label with a confidence score. Even though these results seem to be accurate, the problem is the underlying mechanism of how these models achieve such a detection or any insights that can be used to explain the detection result are now totally lacking from the detection algorithms. There have been some works focusing on shedding lights on the decision or prediction made by those deep neural network-based detection algorithms. These methods mostly works by reverse engineer the black box model and figure out or visualize what is the most important part in an image or a video frame or individual patches that activates those models the most. By doing so, they potentially shed light on some common features that give rise to the detection of the deepfakes. On the other hand, even though these models give us some under the hood information of those detection algorithms, I think the information provided by this kind of methods are still quite limited. So this is one of the major hurdle that this kind of black box detectors, the results from this black box detectors being accepted as a concrete evidence for the authenticity of the media. Right. The second problem for the current deepfake detectors is their lack of robustness to laundering operations and anti-forensics attacks. Now, the laundering operations specifically refers to those operations that were innocuous operations that potentially will be applied to the media for the purpose of them being uploaded to social platforms. This may include blurring of the image, downsizing the image, some additional noise, and most significantly, compression or double compression of the media. So compression out of all the laundering operations is probably the most significant distraction factor for the current detection algorithms. Take, for example, the face swapping videos. If we take the lossless video, most detectors works really well on the lossless uncompressed formats or high quality compressed formats. But we all know that all the videos, when they're uploaded to social platforms like YouTube or Instagram, they will undergo significant compression to reduce the network, the required network bandwidth. And when the videos were compressed into a low quality version, the detection, many of the detection methods will fail. So the robustness to this kind of laundry operation is something that has to be incorporated in when designing or training deepfake detectors. I think more importantly are those specifically dedicated designed anti-forensics attacks. So these anti-forensic attacks corresponding to specially designed signals that are known as adversary perturbations to the fake media, so that when the perturbed media is fed into the detectors, the detector will make an incorrect prediction. Now, adversarial perturbation is a very recent topic in machine learning, and people have shown that past work have shown that deep neural networks, for their delicacy in their structure and the final classification surface, is very much subject to this kind of specifically designed adversary perturbations. Um, so these adversary perturbations usually work by taking the neural network model and compute the gradient of the neural network model with regard to the input image or video frames, and then use that gradient information to design a perturbation direction where the input will be pushed to the other side of the decision boundary. Now, if these methods are designed to be specifically target a detection method, the performance of those defect detectors can be significantly reduced. Sometimes, starting reduce them to like in this particular case, some of this method can reduce their performance from nearly perfect to a little bit better than chance. Okay. So, so it is very important to also study detection methods that are robust with regard to those anti-forensic operations. And there are some recent works going in that direction, where they introduce the idea of adversarial training. So in designing or in training of the neural network-based defect detectors, the adversarial examples created using the perturbation procedure I talked about shortly before will be incorporated in the training cycle. So in that case, the trained model will recognize and will be robust with regard to this kind of adversary perturbations. However, this is far from sufficient because models improved using adversarial training will still this model will still subject to the same kind of attack once its model details are leaked to the attacker. So we need to find some more fundamental solutions to this problem so that the detectors will not be so much influenced by adversarial perturbations. The third challenge, I think, is the lack of generalization to unseen synthetic synthesis models. This is because most of the deepfake detection methods these days are trained on a well-curated data set, which include the deepfake medias usually created with one particular model. So the detectors trained on those kind of data will work really well for these models included seen in training. However, these models may not fare very well in what I borrow the word zero-day scenario from security, when a model just show up out of nowhere, and that's different from all the previous models that have been used in training, and all the existing deepfake models may not work really well for media generated from deepfakes generated from this previously unseen new model. This is a problem that make it very relevant to study the deepfake detection problem is as an unsupervised or semi-supervised problem instead of the traditional conventional supervised classification problem. The fourth challenge I see is what we have when we try the deepfake detectors in the real scenario in the wild, let's say. They usually suffer a high false positive rate. So the false positive rates here correspond to the chance of the detector mistakes real video as a fake video. Okay, and this usually occurs when the ratio between real video and fake video is very high. In the case of on the internet, we may have a rough estimation of this ratio to be 100 to 1 or even 1,000 to 1. In those cases, the detected fake media may actually contains a large number of innocuous real media, and that high false positive rates actually reduce the credibility of the detectors and is a big obstacle for their widely acceptance and applications. So I think that we have to deal with this problem and make the detector work in this kind of imbalanced scenario. So my group have some recent works using a different kind of loss function, loss function that is robust to data imbalance, which partially alleviate this problem. But I think we need a better solution to this. The last challenge I can see for the current deepfake detection algorithm is the fact that detection method always lags behind and work in a passive way. This is because the continuous development, continuous improvement of the deepfake generation technology and the detection algorithms is always in a passive stance where they can only analyze known generation methods. And in that case, we need to actually being able to anticipate the new development of new generation algorithms, and then be more proactive in our stance against those new development, new types of deepfakes. So this brings us to our next topic, which is to get an upper hand on deepfakes. In other words, we want to be more active or proactive in terms of fighting in combating the deepfakes. So this part of the reason is, as I mentioned, is the detection is passive, always lag behind generation. The other part of the reason is deepfakes really grow very fast these days on the internet. So a recent study shown that deepfake making softwares, including Face Swap and DeepFakes Lab, are ranked number 6 and number 9 respectively on GitHub for all the machine learning softwares in terms of downloads and follows. So to put this into context, just think about the top one, the repositories that ranked before this deepfake making softwares are common tool sites like TensorFlow, PyTorch, OpenCV, and so on. So it is quite impressive and kind of alarming to know that deepfake making softwares are heavily used in practice. And from a different source of different information source, here Sensity AI has a survey on the number of deepfakes online. So we have seen this, the number of deepfake videos increases almost double the numbers every 6 months. And a large number of this is of those pornographic nature, which means they are not, beneficial for the society. So that if we just sit on and waiting for the next better generation model for deepfakes, we're not going to be, very effective combating fake media. So we need something that is more active or proactive. Active here means that, we want to influence the generation of deepfakes so that, these models, they will not be as effective as, unobstructed. Being proactive means that we want to disrupt the generation process of deepfake media, and turn the table on the deepfake producers. So there are several developments recently in this direction, go beyond a passive detection of deepfake media. So one is, instead of classifying, just determining if an input media is real or fake, we want also go back to check what model has been used to create that deepfake media. So this task is known also as the model attribution problem. So why is this kind of methods useful? Well, if we are able to trace back to the particular model or model variants that were used to generate deepfakes, by combining that information with a monitoring system on code sharing platforms like GitHub, we may narrow down the scope for the potential authors of those deepfake media, especially those ones that cause immediate personal or societal damage. So, if we can the more we can infer the details of the generation process, the better it will help us to identify the person behind that fake media. So there has been a few works in this area. Most of this method works by embedding the fake media, fake images in this case, into fingerprint space, feature space. And then in that space, we hope to group features, image features, or sometimes known as model fingerprint features, to be close to each other when they come from the same generation model, and differs when they come from different models. In other words, we want the fingerprint features to cluster for the same models. So in that sense, with that kind of model, with this kind of methods, we can trace back, in particular, in this case, which GAN model or which variants of the GAN model has been used to create those face images. We can also take more proactive measures to deepfakes. Here, proactive measures refers to methods that can affect the training and the synthesis process of deepfake generation models. So particularly, we can imagine, we can take advantage of the recent development in adversarial machine learning by embedding perturbations into the training data set. And those contaminated training data set will lead to failures of the training process or the generation process of deepfake models. So one such idea has been explored in two of our recent works. The general idea is to look at the production pipeline, the training and generation pipeline for deepfake face swapping videos, and design adversary perturbations that particularly targeting those critical steps and for the aim to disrupt them. So in our work, we observed that almost all deepfake face swapping video synthesis algorithms rely on a critical pipeline where it starts with face detecting faces in the training or synthesis target videos, and then estimating facial landmarks corresponding to the important locations on faces like tip of the eye, tip of the mouth, or noses, and then align the input face into a standard configuration. Face aligned, cropped and aligned this way will mostly facilitate the training and synthesis process, reduce the training overhead of the neural network. So if we can disrupt or obstruct that process, we are able to affect the training and generation process of this kind of deepfake videos. So our idea is to targeting specific face detectors. Now, face detectors and facial landmark extractors are very common methods in computer vision, very standard methods in computer vision. And most of these state-of-art algorithms also follow similar deep neural network models. So we designed a particular type of white box adversarial attacks to those models, and generate adversarial perturbations that are imperceptible to human eyes or less perceptible to human eyes. At the same time, will disrupt the function of face detectors and landmark extractors. So you can imagine that this method can be used as a plug-in before any of those images, any individual's images or videos being uploaded to social platform, where they can have a little chat box say, protect my data from being used for deepfake generation. Now, this kind of adversary perturbations will be automatically generated and embedded into those media. And when they are used, downloaded and used for training models or generating deepfakes, this adversary perturbation or adversarial noise will take effect and essentially break those processes. So this is what we mean by proactive attacks to deepfake generation and training. So I think, of course, this is only the first step. The active measures and proactive measures to disrupt deepfakes will possibly also induce countermeasures from the side of deepfake generations. If, for instance, the active traces or this kind of proactive adversarial noises are noticed or known to the deepfake generators, they potentially can use mitigating measures to reduce their effects or remove them from the training data. So this just started another cycle similar to generation and detection, where there's another arms race here. So I think in the future, we expect to see more developments in these directions. So that naturally leads us to talk about the future of deepfakes. What is going to happen, and what's the implication for detection? I think in the coming years, there will be a few trends in terms of deepfake generation that we should be particularly aware of. I just summarized them into the following items. I think, first of all, the generation will become more efficient. Even real-time or near real-time generation is possible. Then we're expecting to see large number of deepfake videos deepfake media, image, audio, videos online, and with improved quality. Also, I think there is a trend to go more realistic multimodal personalized synthesis. So these days, I think as we'll see shortly, the cutting edge technology in deepfake generation has gone beyond simply creating an image of a random face or swap faces between two different individuals. Things are going into the direction more and more of cross modality. So you may have a piece of text, the text, based on the text, we generate a piece of speech, and personalize for a targeted person. And then that's based on that speech, we can create a video of that person's face speaking those words, right? So we are going to see this kind of more comprehensive forms of deepfake medias, go beyond just simple images, audios, and videos. Also, I think the real danger, or the kind of important advance in deepfake generation is they are going to merge with the 3D real world things. Right now, deepfakes have a lot of artifacts because they're essentially created, at least visually, from 2D signals. But if we are um, if this is combined with 3D generation, then that will pose a lot more challenges for detection algorithms. Currently, we simply do not have detection algorithm for that purpose. I'll use one of the recent incidents of deepfakes as a motivating example. You may have seen this fake Tom Cruise video fake Tom Cruise videos that were circulated on video sharing platforms like YouTube and TikTok. Okay, these videos were actually created using based on an imposter who has very similar physique as Tom Cruise, the real person. On the other hand, this series of deepfake Tom Cruise videos look very highly realistic, and very difficult to tell apart from the real person. Now, according to the authors, to the author of this set of videos, these videos actually were created using an open source tool for deepfake face swapping video generation. But what differed this time is his team take extreme efforts to fix and perform manual post-processing on the created videos, almost frame by frame, to remove those artifacts as well as potential traces that can be used for detection. So the end result is a highly convincing, a set of highly convincing videos. Not only human viewers cannot tell them apart when we actually input these videos into the deepfake platform, let it run over all the methods we have integrated into the platform. None of the methods can reliably detect or consistently detect these videos as deepfakes. So that's the partly reflect the fact that deepfakes, the detection of deepfakes are only successful for those cases where very little or no post manual processing is involved. For a dedicated deepfake generator, they can still use all this manual work to remove those artifacts. One side note I want to mention is these videos are actually, even though they're very realistic, a lot of the artifacts can still surface when you play them with slower playback mode, playback speed. So like in this particular case, you can see that the eyeglasses actually was missing from some of the frames. So they're not perfect, but still, they're very impressive and difficult to detect. Even use the state of the current deepfake generation algorithms. Another important trend in deepfake synthesis is reduce the requirement on data. So traditionally, either we do face reenacting, or face swapping. We usually need videos as the source and the target. Now, some of the recent development in computer vision and graphics is to reduce the reliance on those data. So what is shown on the slides is one example of such works. This method is known as the first order motion. As you can see, they take a driving video and animate a single face. Some of these faces corresponding to a person. We do not have any video footage like Mona Lisa. Nevertheless, this model is able to animate those still faces and create a video sequence out of a single image driving by the source video. So this kind of techniques can be used to create real-time deepfake uh, deepfake videos using anybody as the target. Another interesting work in the direction of real-time deepfake synthesis, face synthesis, comes from NVIDIA research. In the recent work, Face VID to VID, we've seen that an original video can be represented using a GAN-style model to resynthesize the faces of different viewing angles. So as you see, I used Ryuzen's face, and there's an online demo tool for that. And I used Ryuzen's face, and you can see the rendered image actually looks very realistic. Okay, and this algorithm has very efficient running time, and this is something we have closest to a real-time personal presence. Okay. Now, there are also several developments, recent works on multimodal deepfake generation. So one of this work is known as wave to leap. So what it does is take an input video like this one, and
I'll go around. Wait for my call.
And take this audio as another input, and then we'll generate the shape of leap in the input video, and create a video, adopt video using the input audio. The result is like this.
I'll go around. Wait for my call.
So this technology, as you've seen, can create very realistic way lip syncing videos. Basically, take any video, and they also the paper claims you can take any input video and input audio and putting them together to create such kind of adopt video. Another work from Stanford University have demonstrated a new method that can edit and synthesize a video based on an input text. So here is a demo of this method.
Here we replace "Wherefore art thou" with "Why are you?"
Oh Romeo, Romeo, why are you Romeo?
And here's another edit.
I love the smell of napalm in the morning. I love the smell of French toast in the morning.
Note that the synthesized words were not spoken by the subjects in the training video. The audio of the new words were separately recorded.
So as we've seen here, we can actually take input from any text and then put those texts into the voice and faces of a target person. So this kind of method will bring the realism of the flexibility in editing and the controllability in editing of those deepfake videos to a whole new different level. Not only we can synthesize using deepfake synthesized faces, we are also able to make the creating sequences of whole body movements. So this comes from a recent work by a group of authors from UC Berkeley called Everybody Dance Now. So you can see that it based on an input source video of a person, a person's movement. It creates a target video, recast the same set of body movement to a different person and create that video sequence. Now, deepfakes are not only limited now to faces and human bodies. We actually have seen a generalization of the deepfake synthesis algorithm for other type of objects and scenes. The most recent work coming from, again, NVIDIA Research Lab have shown that using StyleGAN type of models, we're able to create natural and human-made man-made scenes, in this case, churches or different kind of objects, cars, and in-room scenes. So combining all this synthesis technology with the face synthesis technology we have seen before, we probably can create the whole scene with someone present there. Okay, and also very recent work on this neural radiance fields or NERF open up new opportunities for deepfake synthesis. Put very simply, the NERF model is to recreate a 3D scene from a few of photos using deep neural networks. Now, the neural network, this NERF model is very effective in capturing all the fine details of the 3D scene and then being able to re-render scenes at different viewing angle. In this case, the two examples I shown here, just from a few photographs of the images, we can actually recreate the whole 3D scenes. Now, this, if combined with all the previous capacities we have seen, generating human faces, human voices, natural scenes, and other kind of objects, then in the future, we're probably seeing a lot more realistic deepfakes that bring the kind of artificial irreality to a new level. Okay, and that, I think, brings in a new set of challenges for detection algorithms and digital media forensics researchers. So we have to continuously come up with new methods to be able to handle all these different new developments. All right, so we reached the end of this tutorial. I hope in this process we have convinced you that AI algorithms are now becoming very powerful and can create highly realistic synthetic media, and we call them deepfakes. And there are potentially real damages and significant damages related with that can be caused by this type of deepfake media. Researchers, including ourselves, working in multimedia forensics, are doing our best to develop new technologies to detect and obstruct these deepfakes. However, the competition between foundry making and forensics is a perpetual cat and mouse game. So each one is trying to improve so that can better handle the new development from the other side of the camp. So I personally do not see this to have any clear winning side in the near future, simply because this is a very dynamic competition between the two different groups. But one thing I want to add on as the last words is the fact that fighting deepfakes is not just a technical problem. Actually, the problems caused by deepfakes is deeply rooted into our current online culture, and there is a complicated social technical problem. The solution, of course, will come from part of the solution will come from the research efforts, detection algorithms and all these other mitigation methods we have covered in this tutorial. But it also requires a joint collaboration effort from all across the society, including the academia, non-STEM social science, psychology, social psychology, also from social network platforms, government agencies, and media. And even every single online user will have an important role to play here, to just play our active part to stop or slow down the spread and dissemination of deepfakes. Okay, so this will be what we cover in this tutorial. We would like to thank our collaborators, and we're happy to take some of the questions. Thank you very much for your attention.